Hello everyone, my name is Nikola Zubic. Currently I'm a MPhil student in computer science at Faculty of Technical Sciences, University of Novi Sad. Today I will be discussing my latest work entitled An Effective Loss Function for Generating 3D Models from Single 2D Image Without Rendering, a work done with Professor Pietro Leo from the University of Cambridge concerning the problem of single view 3D reconstruction. So, to introduce the problem, one of the main problems in 3D computer graphics and vision is the ability of a model to learn 3D structure representation and reconstruction. In supervised deep learning, we have a direct learning from 3D data representations such as meshes, voxels, and point clouds. They require a large amount of 3D data for the training process, and also their representation is sometimes very complex for the task of direct learning. And these factors lead to the abandonment of this approach because of its inefficient performance and time consumption. Unsupervised 3D structural learning learns 3D structure without 3D supervision, and a novel field which is available here is called differentiable rendering. This allows the gradients of 3D objects to be calculated and propagated through images, and it also reduces the requirement of 3D data collection and annotation while enabling a higher success rate in various applications. But these evaluation techniques are very time-consuming because their loss functions are based on differences between RGB pixel values, and by rendering the predicted 3D structure from a specific viewpoint and then evaluating the loss function based on pixel-wise loss between rendered and ground truth image, model parameters are optimized to reconstruct the desired 3D structure, and this takes a lot of time. So they don't contribute at all to an accurate 3D structure reconstruction, and we would like to have a method that is faster in that sense. So here is an overview of our method. Our method basically, which we can see on the upper image, removes the rendering process and requires only 2D projections of 3D point clouds. So during the generation of 3D shapes using multiple silhouette images from different viewing angles, 2D projections of all points on the shape should uniformly cover the silhouette from each viewing angle. And we implement this by using two key ideas, and these ideas together form effective loss function. So the first is that for 3D shapes formed by 3D points, their projections for each view should locate within the silhouette, and all projections for each silhouette should distribute uniformly. So we achieve this by maximizing the loss between each of the pairs of these 2D projections. As we can see on the image below, when we produce the output, we get the point cloud representation, which is this teddy bear, which is this first teddy bear. Secondly, we use the Poisson surface reconstruction in order to get a 3D mesh, and then we use a GAN method in order to retrieve the texture. By this, from one 2D image, we are able to create a 3D model. So right now we're going to talk about the implementation details. Our goal is to learn the structure of 3D point clouds, which are formed by n points. We will say that they are nj, only from GT ground truth images of the silhouette SI. Here, j goes from 1 to n, and I goes from 1 to GT. And projection of every point nj, so these are the points that together form a certain point cloud because we have a point cloud representation. In view I, we will denote them with pij, and the error we want to evaluate how well the sets of projected points cover the silhouette. So our loss will be basically composed of two parts. Here we see on this image the left and right grids. They basically represent two ground truth silhouette images, SI, and NJ point projects onto an image, and its projection is PJ. So for 3D shapes formed by 3D points, their projections for each view should locate within the silhouette, where the whole white grid is a silhouette and its pixel values are 1. these red squares. So we are basically minimizing differences between pixel values of projections and 1 for every projection. This is on the left grid, on the left image, and on the right grid we must not only minimize the first term loss but also the second term loss, which maximizes the distance between two different point projections from a 3D point cloud, Pj and Pj prime. The pixel value of every projection Pj we are going to denote by Pi. The first term here will penalize all the points outside of the foreground by calculating this difference, 1 minus Pi, and we assume that the foreground in the binary silhouette image has a value of 1, as we previously said. So, when we use this, it is impossible to force all projections into the foreground by minimizing this L1 norm. If we optimize point cloud according to some silhouette image, as we can see on A, and start from some randomly initialized points B, then we will get inadequate point projections if we use this norm. So there are two reasons why this problem occurs. One reason is the fact that L1 norm is non-differentiable. Even if we look at the difference only. The second reason is that we only examine the pixel intensity based on the difference between 1 and the interpolated pixel value Pi. Based on the four closest binary pixel values, and this prevents training if the projections are too far away from the foreground. And our goal is to produce non-zero gradients anywhere in the background part, while the pixel values in the foreground part do not require a modification. And we do this easily by using the negative sign function. We will denote all the images, all the pixels of all the images that are modified by this by Pij. So basically we use this modification, and after using this modification, we are able, when we are given a silhouette image, for example A, and randomly initialized projections B, we are able to force these projections into the center of the silhouette by minimizing this modified first term loss function. So idea was to generate a progressively varying field. And the problem with this is because these points right now do not cover the silhouette image perfectly. We would like them to be uniformly covering the whole silhouette. And we do this by using Gaussian function to obtain a loss based on the invariance of the structure. So for each projection Pij, the loss based on the invariance of the structure will model its spatial relationship with all other projections Pij prime. And the idea here is that we want to have the projections that will uniformly cover the whole silhouette. So they are right now in the center, as we saw in the previous slide, and with this L2 loss, they will be perfectly covering the silhouette. So this here L2 loss, as we can see, these Wij and Wij prime are weights that correspond to the projections Pij and Pij prime. This theta parameter is a decay parameter. He is greater than 0, and μij, which is also greater than 0, is the boundary bias for the projections Pij. Wij expresses to what level the projection Pij merges with the background. And if that weight is set to 0, of course this projection is such that the invariance of the structure is completely removed. So that the modified first term loss immediately forces Pij within the foreground. And this decay or merge parameter controls the merge interval, so basically the intensity of the invariance of the structure of a given background 3D model, and the projection boundary bias μij for some certain projection Pij basically controls the distance to the foreground's boundary where the invariance of that projection reduces. At the end, we form the finally we form the effective loss function EL through simultaneous minimization of the modified first term loss function m1 and the second term loss function L2. We use the following data sets. So basically we used ShapeNet dataset, CAB-BERT dataset, and Pascal 3D Plus dataset, which has various 3D objects. For the numerical evaluation for point clouds, we use the Ampère's distance. Basically, here we calculated the Ampère's distance between predicted and real or the ground truth point clouds. Volumetric IOU comparison is used to compare the 3D grid voxelized from the predicted point cloud with the one that is voxelized from the ground truth point cloud, and for the texture evaluation we used the Frachet inception distance FID. Here are the results. So in this first table, upper table, we can see the quantitative results on shape prediction with non-camera pose on the ShapeNet dataset, and we report the Ampère's distance between normalized point clouds multiplied by 100 in order to get to not have something like a 0 point and so on. And we use three categories: airplanes, cars, and chairs. And our point cloud output outperforms all the other methods in terms of Ampère's distance. Here, lower value means better, means that our point cloud prediction is more similar to the ground truth point cloud prediction. Here on the second table, our results outperform state-of-the-art differentiable renderers in the volumetric IOU, while simultaneously being less time consuming during the training phase. We will see that on the next slide. And for cars, our outcome is better than renderers based on voxels, but as we can see, it's very similar to renderers based on meshes, because meshes represent a superior initial 3D representation for large areas of flat surfaces. Here we see that in terms of training time, we also outperformed all the other. Implementation data and trained models are available at the link. We currently have about 90 stars. And we perform detailed case study, which can be seen in appendix of our paper at AIAI. So also, here are some of the results that we have. These are the visual results. Basically, we use real-world 2D bird images as input for generating a 3D model, and in the first column is the input, where we have an image of the real birds. They are, for example, taken from internet, and in the second column this is a generated 3D mesh which is obtained from 3D point cloud after Poisson surface reconstruction, and in the next four columns there is a predicted 3D model which is visible in four poses. And here we have the qualitative results on Pascal 3D Plus dataset and CAB-BERT's dataset. CAB-BERT is on the right, and on the left we have Pascal. Each object has been rendered from three views, and the top row represents the texture learned by GAN. So basically, in this paper we proposed a 3D reconstruction based on a single image, a method for learning the pose and shape of 3D objects, given only their 2D projections, using the initial point cloud representation and then converting that representation to a 3D mesh. Mesh is textured using GANs to produce a final output, and extensive experiments have shown that point clouds compare well with the voxel-based representation, such as performance and accuracy, and the proposed framework learns to predict shape, texture, and pose from single images without rendering step, based solely on 2D projections of 3D point clouds and their coverage of the ground truth silhouette. While rendering requires exhaustive computation, our key finding is that it does not endow accuracy in 3D structural learning. Thank you all for listening to this presentation, and don't hesitate to contact us if you have some ideas for the collaboration or some more in-depth questions about the paper.